Good morning. It's my pleasure to give the first contributed talk of this conference. My title is Late Population 3 Star Formation During the Epoch of Reionization, and my co-authors are listed here. Let's see, how do I advance? Is this? Sehr gut. Okay, so this is results from a paper that appeared very recently in the Astrophysical Journal. Full title, Late Pop 3 Star Formation During the Epoch of Reionization, Results from the Renaissance Simulations. So I'm going to start out by talking a little bit about the Renaissance simulations, which we've carried out over the last few years, which provide a lot of new information about the properties of the first galaxies. And then I'll get to the topic of this talk. So these are very high resolution adaptive mesh refinement radiation hydro simulations that we've carried out on the Blue Waters supercomputer at the University of Illinois. Very powerful machine. And what you see here are, so these are a suite of 3 simulations of statistical volumes sampling different density environments in the early universe. Here you see the dark matter, here you see the hydrogen, and you see H2 regions being generated by multiple first galaxies. So these simulations took roughly 50 million core hours and yielded a sample of over 3,000 first galaxies. And what's unique about these simulations is that we start with the population 3 mini-halos and include their formation and feedback effects, which is very important to get the properties of the first galaxies right. So the 3 environments are actually taken from a single cosmological realization in a 40 megaparsec box shown here. And within each of these these black boxes, we have very high resolution in the initial data, effectively 4,000 cubed. We then use adaptive mesh refinement to get down to a finest resolution of about a parsec proper. The particle mass is shown there, and that gives us a very good coverage of the halo mass function. We're more or less complete down to 5 times 10 to the 6 solar masses, and then it starts to roll over a little bit. But we have very good coverage above that, all the way up to a few times 10 to the 9 solar mass. I'm not going to go through this in any detail. I just wanted to mention the physics in the simulation. We're doing 9 species primordial gas dynamics, forming molecular hydrogen. The cooling includes the primordial gas as well as metal line cooling from the enriched gas. We're doing radiative transfer using ray tracing for both the ionizing radiation as well as the photodissociating radiation. And we also include Lyman continuum radiation pressure. We've actually done 7 of these simulations. We've done some environments 2 ways, one with and without a Lyman-Werner background. Now, the star formation is, of course, key to this whole business, and what we do is summarized here. This is from these papers by John Wise and Tom Abel. So basically, you test for collapse, and we use a high density threshold and a threshold on the molecular hydrogen fraction of 5 times 10 to the minus 4. And then based on the metallicity of the gas, we either form a population 3 star, an individual star, or we form a metal-enriched star cluster. For the PopIII stars, we draw the initial mass from a Krupa-like IMF with a characteristic mass of 40 solar masses. And then based on that mass, we calculate lifetimes and feedback effects based on published literature, lifetimes, yields, endpoints, and so forth. After a star ends its main sequence lifetime, we do track the remnant so that we know where it goes, and we can write other papers about that. In the case of a star cluster forming from metal-enriched gas, we assume it has a saltpeter IMF, and we do a time-dependent feedback of both energy and metals. So we've been writing a number of papers based on the results from these simulations. Again, mostly focused on the properties of the first galaxies, but because we include the population 3 mini-halos in the simulation, we can look at them as well, and that's what I'll be talking about for the remainder of this talk. So here is the population 3 star formation rate density in the 3 simulations. Redshift, time is moving to the left, redshift high, redshift low. And here you see the rare peak simulation, the average, and then the void simulation. These simulations are so time consuming that we simply stop them at some point because we can't continue them any further. And so for the rest of this talk, I'll be focusing on the void simulation, which we've run down to a stopping redshift of 7.6. And what you see is that population 3 stars form continuously, but at a low rate until we stop the simulation. So this is a projection through the void simulation region, about 6 megaparsecs on a side, co-moving, a volume of 220 cubic megaparsecs. And at this stopping redshift, we find 14 population 3 systems. Over here, I'm plotting a projection of the Lyman-Werner radiation intensity. And this is in units of 10 to the minus 21. So 10 to the 0 is 10 to the minus 21. CGS units. And you see that most of these systems form in high radiation environments. This is a table from the paper, 14 systems, and over here is the radiation intensity in units of 10 to the 21, 10 to the minus 21. And you see that these numbers are all around unity. Some are even as large as 11. So they're forming in high radiation environments. This shows the actual number distribution. So what is shown here is the halo mass function. The blue bars are unenriched halos. The green bars are chemically enriched by previous star formation. And the red shows the halos that host new population 3 stars at this time. And you can see that they are forming, they're not forming in the lowest mass halos. They're forming above about 10 to the 7.3 solar mass, all the way up to 10 to the 8 solar masses. So they're forming in rather massive primordial halos. And you might ask, well, how is this possible? How can they form at all given the strong Lyman-Werner radiation? And the answer is provided by earlier work that I did with my student Brian O'Shea, and Tom Abel and John Wise also looked at this. And what we showed in this 2008 paper is that you can achieve collapse of the primordial cloud core in strong radiation environments if the halo is massive enough. So this shows the virial mass of the halo at the point where you you move beyond the loitering phase of population 3 star formation. You get the actual gravitational collapse. And here is the radiation intensity. So this is a tenth of 10 to the minus 21, and here is 10 to the minus 21. And you see that if you're at or above 10 to the 7 solar masses, you can achieve collapse. And the physics is straightforward. Of course, you've got photodissociation, but the production rate of H2 is temperature dependent. And so in the more massive halos, you have higher virial temperatures, higher production rates, and you're able to offset the photodissociation with production. So this is showing that even at 10 to the minus 21, you're able to collapse at 10 to the 7 solar mass. We have somewhat more massive halos here. So the other interesting result is that if you look into these 14 systems at redshift 7.6, this is a table showing the number of young, i.e. active population 3 stars at that time, and they vary from 1 all the way up to 18. Now, because we draw their initial mass from this mass function, we get population 3 stars as low as 8 solar masses and as high as several hundred solar masses. Of course, their lifetimes, their luminosities, their chemical yields depend upon their mass. But young means that they're still in their main sequence lifetime contributing radiation. Here is the mass in young stars, and this one here is the winner with over 1,000 solar masses of young stars. This column here shows the population 3 remnants in those same halos. And so after they finish their main sequence lifetime, they just become passive remnants that we can track. So our motivation for looking at these low redshift population 3 stars came from this interesting discovery last year by Sobral et al., written up in the New York Times, illustrated beautifully here. Who needs the James Webb Space Telescope when you've got astronomical artists? But they speculated that, the authors speculated that this object, CR7, the brightest Lyman alpha emitter at a redshift of 6.6, contains a blue component that might be a massive population 3 star cluster. So here's what it actually looks like to the Hubble Space Telescope. This is the red component, and this is the blue component that the authors speculated was a massive population 3 star cluster. What we did was we took this output from the Renaissance simulation and looked to see whether there were any analogs to CR7 in the volume. So this was the most massive system. This is a dwarf galaxy. Here, these black dots are individual star cluster particles. And up here is the population 3 system. This is the virial radius of that halo. This is density, this is the Lyman-Werner radiation, this is the metallicity, and this is the temperature. And you see that this is forming in very low metallicity gas, a pocket of low metallicity gas, sort of down around 10 to the minus 5 solar. And it's about 10 kiloparsecs away from this luminous galaxy. But if you look at the properties of this system, which is outlined here in red, you see that it's nowhere near the luminosity of CR7. So this is the luminosity, the UV luminosity of the population 3 system, 10 to the 40 ergs per second. This is the luminosity of the neighbor, 7 times 10 to the 42. That's a factor of 100 fainter than the CR7 red component. So this looks like it is not anywhere near as bright and massive as the observed object. So here I am at my conclusions already. I'm going to leave plenty of time for questions. The population 3 stars do continue to form at low rates in pristine gas, even as low as redshift 7.6. I think if we could have continued the simulation, it would have just kept on going. This confirms earlier results by Muratov and Trenti. We find that multiple PopIII stars form in these more massive halos. You simply have more primordial gas because they're more massive halos. And the criteria that we use in order to create a PopIII star just makes multiple stars. These are not tight binaries. These are just individual, widely separated stars. We have 14 of these PopIII galaxies at the end of the simulation, but no systems are anywhere near as massive and luminous as CR7. And as we examine how these galaxies are formed in the Renaissance simulations, we see that once you've made a population 3 star in a halo, it doesn't remain pristine very long. Very soon it becomes enriched by its own supernova ejecta, and then you start building up the dwarf galaxy. So it's very hard to understand how you could have 10 to the 7 solar masses of PopIII stars forming in a burst would be required to explain the CR7 blue component. So we think that that's probably not what we're looking at. Thank you very much. I'd be happy to take questions now.
There's a Lyman-Werner background, right? So how do you build the background in these different boxes? Is it the same background on all 3 of them, or each one of them has a separate?
Are you asking about the Lyman-Werner background?
Yeah, Lyman-Werner background. How is it built among those 3 different, how it's spread among those 3 different boxes?
Yeah.
Are they feeding the same background, or are they just independent boxes?
Well, we calculate both the direct radiation from neighboring galaxies as well as the Lyman-Werner background. The Lyman-Werner background we derive from the average region simulation. So we calculate it from that. But we're only able to run that to redshift 12. So we only have, so if I could have my slides again. If I could just bring those up again. So here's the void simulation done 2 ways. Here now redshift is decreasing to the right, so I've switched things on you. And you see that we've got one curve with a Lyman-Werner background derived from the average region simulation. And then we've got one with no Lyman-Werner background. What we find is that the local radiation from PopII galaxies dominates most of these systems. And so the Lyman-Werner background doesn't seem to be very, very important here.
Okay. Do you also include the effect of X-rays on the formation of molecular hydrogen?
The effect of what?
X-rays. X-ray
X-rays.
partial ionization, yeah.
No. We've written some papers where we post-process these simulations and calculate an X-ray background and see what it does on the intergalactic medium. But no, we do not modify the H2 formation rates. That'd be an interesting thing to do.
Thanks.
Okay. So we have very beautiful result, but I would like to ask you about the the multiplicity of faster forming star cluster. So in your simulations, that clusters are typically small, about the number of 10 or so. But in the Stacy and Volker Blom's result, Takashi presented in the previous talk, it was typically more sort of higher multiplicity, about 50 or even more.
Right,
so
right.
What do you think the cause of those difference?
Well, our multiplicity is a different thing from what you're describing. You're describing the fragmentation of the protostellar disk. We don't have that resolution. We're simply looking at the cold gas in the halo, and
I see.
we draw the mass from this IMF, and if we draw a low mass, then there's a lot of this primordial gas left. And our algorithm will just create another star, in the next time step.
Okay, so the fragment in your simulation are more massive than the others that Volker result.
I mean,
how massive are they typically?
Oh, the most massive one is I like 300 solar masses.
They are quite massive.
Let's see.
Okay, I understand. So they are dense cores rather than protostars.
That's right, exactly. Let's see. It's way over on the left.
Okay, thank you very much.
Yeah.
So I see no further questions, so let's thank Mike again.
Thank you. Thank you.